Hello everyone. So let's now solve question number 3. Consider the following two groups. In group 1, there are three functions from one vector space to another, and in group 2, there are three properties of the functions. All the vector space have usual addition and scalar multiplication. So in group 1, we have given three functions, and in group 2, if we clearly see, these are basically the condition for any given function to be a linear transformation. And the third option is that T is a linear transformation. So we have to choose a set of correct options that which function satisfy which property from group 2. So even though we can clearly see that R is a linear transformation as it is x plus y plus z, which is a linear space, and it is a scaling by 1 by 5. So R would be a linear transformation. But anyway, let's see each group one by one. So let's start here. For P, given that q of xy is equal to x squared by y comma y if y is not equal to 0 and x comma y if y is equal to 0. So for first condition, that is t of v1 plus v2 equal to t of v1 plus t of v2, consider our v1 vector to be 1 comma 1 and v2 vector to be 1 comma 2. Then t of v1 with respect to this, as y is not equal to 0, would be just 1 comma 1, and t of v2, again we will take this definition as y is not equal to 0. So this would be 1 by 2 comma 2. Now if we take t of v1 plus v2, that is 1 comma 1 plus 1 comma 2, so that would be t of 2 comma 3, and again y is not equal to 0, so we will take this definition. So this would be 4 by 3 comma 3. Now we have to check whether t of 2 comma 3, that is equal to 4 by 3 comma 3, if this quantity is equal to the summation of these two vectors. But we can clearly see that if we sum these two on adding, we will get 3 by 2 comma 3. As these two are not equal, so P does not satisfy the first condition. So clearly it will also not satisfy the last, that is T is a linear transformation. Now let's check for the second condition for P. So for second condition of P, second condition. Now first check the scenario for y is not equal to 0. So here as we are trying to disapprove the statement, so that's why we took example. But this time now we are trying to prove the statement. So that's why we will follow this procedure that t of c times some x comma y. Here we are considering the case y is not equal to 0. This would be as respect to the given transformation t of cx comma cy. So this would be c square x square by y comma cy. Right now, so here to be cy. So now this that this c will cancel out. So now we will left, we can take c common, so it would be x squared by y comma y, and that is exactly our linear transformation here that's given here. So this would be c times t of x comma y. So for y not equal to 0, this property is satisfied, but let's also check for y is equal to 0. So now consider the case for y equal to 0. So that is t of cx comma y, t of cx comma cy. So in the case when y is equal to 0, our transformation is x comma 0. So it would be t of cx comma 0. And again we can, sorry, this would be cx comma 0. The t will not be there. We can take c command, and it is again we got t of x comma y. Okay. So in both the cases when y is equal to 0 and y not equal to 0, the second property from group 2 is satisfied. So if you check from the option, P satisfy 1 but not 2, that is incorrect. P satisfy 2 but not 1, that is correct. And P satisfy 3, that is incorrect. Now similarly, we will check for Q. Okay, for Q, the transformation given to us is x comma xy. So we have given that Q of xy is x comma xy. Now again, for the first property, that is T of v1 plus v2 equal to T of v1 plus T of v2, consider the vector v as v1 is 1 comma 2 and v2 is 1 comma 1. So T of v1 would be, from this we will get 1 comma 2. T of v2 would get 1 comma 1. T of v1 plus v2 is equal to T of 1 comma 2 plus 1 comma 1, and that is T of 2 comma 3, and that would be 2 comma 6, while T of v1 plus T of v2 is 1 comma 2 plus 1 comma 1 that we got here, and that is 2 comma 3. So clearly these two are not equal, so that means the first property is not satisfied by Q. Now if we check for the second property, so that is T of C times x comma y is equal to C times T of x comma y. So this for the second property. Let's take the vector v as 1 comma 2 and c to be 2, and if we try cv, then we will get T of 2 times 1 comma 2, and that is T of 2 comma 4, and that would be 2 comma 8. And now if we tried finding C of TV, this would be 2 times T of 1 comma 2, and that would be 1 comma 2, and that would be 2 comma 4. And as you can see, these two are not equal, so second property is also not satisfied by T for the Q. So as both are not satisfied, even if one of them, then in that case also the T is not a linear transformation. So for Q, all three are false. So Q satisfy 1, that is false. Q satisfy 3, that is also false. Now for R, let's verify our assumption. So R was given to us as T of x comma y comma z equal to x plus y plus z by 5. So take v1 as x1, y1, z1, and v2 is x2, y2, z2. So T of v1 plus v2 would be T of x1 plus x2, comma y1 plus y2, comma z1 plus z2. So that would be x1 plus x2 plus y1 plus y2 plus z1 plus z2 divided by 5. And if we try rearranging the term, then we can write it as x1 plus y1 plus z1 by 5 plus x2 plus y2 plus z2 by 5. And this quantity here is nothing but T of x1, comma y1, comma z1. And this quantity here is T of x2, comma y2, comma z2. So the first property is satisfied. Now let's check for the second property. That is T of Cv equal to C times T of V. Consider V to be some x, y, z. So T of Cv is equal to T of Cx, comma Cy, comma Cz, and that is equal to Cx plus Cy plus Cz by 5. Taking C common, we get x plus y plus z by 5, and that is nothing but T of x, y, z. So the second property is also satisfied. And as both the properties are satisfied, R is a linear transformation. So for R, all the three are satisfied. So R satisfied 2, R satisfied 3, R satisfied 1 but not 2. That is incorrect as R satisfied all the three. Thank you.